Good afternoon, everybody. My name is Brianna Horton. I am the protocol officer here at Goddard Space Flight Center. I'd like to welcome you today, both in person and virtually, to our first Engage session of 2025 to celebrate OSIRIS-REx and the results that we have found from the sample return.
I think one of the age-old human questions, perhaps going back to the beginning of humanity, is, are we alone in the universe? And that maps directly into, why are we here?
OSIRIS-REx is 3 missions in one to make that kind of exploration cost-effectively for not much more than the price of a blockbuster movie.
There's been nothing like OSIRIS-REx in NASA's repertoire. I like to call it the Daredevil spacecraft. We're going back to the dawn of the solar system. We're looking for clues as to why Earth is a habitable world. And of course, the biggest question, the one that drives my scientific investigations, is the origin of life. What is life? How did it originate? And why was the Earth the place that it occurred?
10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1.
Now, I would like to introduce Dr. Jamie Cook, who is our acting director of the Solar System Exploration Directorate, to introduce the panel and kick it off.
Thanks. That video always makes me really emotional. This is such an exciting mission. NASA's OSIRIS-REx asteroid sample return mission stands as a groundbreaking achievement in space exploration. This mission really exemplifies what can be accomplished when industry, academic institutions, and government agencies collaborate towards a common goal. On September 24th, 2023, OSIRIS-REx triumphantly returned its precious cargo to Earth, 121 grams of asteroid material, more than doubling the mission's original goal of 60 grams. Careful planning and precision engineering allowed the team to overcome many surprises on their journey to Bennu and back. For example, the first pictures of asteroid Bennu's surface revealed a rocky terrain covered in boulders, not the fine-grained materials the scientists had expected. The mission mapped the asteroid for a year and used these detailed maps to program the spacecraft to navigate to the surface of the asteroid, a technique more precise than the one they had planned to use. Once the sample was on the ground, the curation team at NASA's Johnson Space Center opened the sample return capsule, ensuring that every grain and pebble was preserved in its pristine state. Thanks to their dedication, scientists around the world now have an unprecedented opportunity to study material unchanged since the earliest days of our solar system, without interference from Earth's environment. This mission's success is a testament to global cooperation in space exploration, and I'd like to extend my gratitude to our Japanese colleagues in the room. Their contributions through JAXA's Hayabusa 2 mission have significantly advanced our collective understanding of the cosmos. In the spirit of collaboration, JAXA has shared their Ryugu asteroid sample, and in return, NASA has shared a portion of the Bennu sample with Japan, further amplifying the scientific discoveries these missions can provide. So please join me in congratulating the entire OSIRIS-REx mission team on this historic achievement. And this afternoon, you're going to learn about exciting mission science results, and I'll turn the presentation over to James Traley to introduce our panelists and welcome our panelists up.
Awesome, yeah. So let everyone take the stage here. So yeah, I'm James Traley. I'm one of the planetary science producers here at NASA Goddard Space Flight Center. Wanted to welcome you all in for our panel discussion about the incredible OSIRIS-REx sample results. So with us today, we have Jason Dworkin right here next to me. He's the OSIRIS-REx project scientist here at NASA Goddard. We have Harold Connolly, who is the OSIRIS-REx mission sample scientist from Rowan University. He's a professor there. And then we also have Amy Simon, who is the osiris-apex, our new extended mission to Apophis, the Apophis Explorer. She's a project scientist here at NASA Goddard. So Thank you for joining us today. And so one quick note, that trailer that you saw at the beginning of this panel discussion, it's for a film that is actually now released on our new streaming platform, NASA Plus, plus.nasa.gov. So if you wanted to relive the thrill, the excitement, all the twists and turns, the surprises of our mission to Bennu and back, you can watch that now. It's now available, leading all the way up to today, this moment of sample return and getting the sample back. And so first, I just wanted to kick things off by asking our panelists where you were on September 24th, getting this sample back. What was your experience? What was it like? You know, years in the making, finally seeing the sample. I'll start with Jason, because we actually have a photo of you where you were from that day, if we can pull that one up too. There we go.
Yep. that was the next day. That was the next day, making sure the sample was brought back to Johnson Space Center under the greatest care and supervision. So I actually had 3 jobs on the day of sample return. I was back up to go in the field in case one of our field scientists was unable to go out and recover the sample and make sure that, check the environmental conditions. I was in the ops room there to make decisions in case something went wrong. Actually, a 4th thing, I had to run and give an interview as soon as the sample landed. And then I was also the heavy for curation. I had a different shirt to wear to make sure that people very excited about the science didn't get too close to the sample. Harold?
So, yeah, I had one job with 2 main components, 3 if you consider morale, to continue to help people to stay calm at all times. So as mission sample scientist, when I was at the actual return, I was in the operations room with Jason. So a lot of people were behind the scenes doing many things to help make all the wonderful television and the actual return process work smoothly. So television, the back of my head is famous because that's all you saw of me the whole time. And then after the sample was brought to the temporary curation facility by our outstanding team, the outstanding curation team took over. And my job was to stand in the little area and watch everything that was going on with curation and to make decisions for science if they were needed. So a few time periods we had to decide if we were going to sweep up something with a specific kind of vacuum, one type or another. So I had to concur with all those processes and of course just be excited as we were after 20 years for you at that time period?
At that time, it was 20.
Yeah, and 14 years for me or something like that, yeah. Amy?
So my role on the mission was really on the remote sensing side before we picked up the sample, so I didn't really have a role in the sample return. So I was actually back here at the visitor center for the live viewing event, biting my nails as that parachute didn't look like it opened and then opened. So I was hoping not to have to be the face of that if things didn't go well. So it was you know, a jubilant, exciting experience, mostly watching the back of Harold's head.
Yeah, and I was doing the play-by-play commentary for the broadcast, and I had to keep talking. My heart was racing, and I was just looking for the parachute to deploy, kind of trying to keep sane the entire time. So, a wild day, and you know, it kind of speaks to the testament for this mission, just how incredibly complex it was to achieve this amazing goal of bringing a sample back. And we often get the question, well, why do we try to do something like this? What's the point of going all the way out, you know, getting this sample when we have pieces of meteorites that land here on Earth all the time?
I want to say, James, we had 2 big monitors in the operation room with lots of different splits for different cameras and everything else that we were watching. And one of them in a small corner was you most of the time, giving us the blow-by-blow from the outside. So thank you for that.
Yeah, my pleasure. Yeah, so why did you have to put me through the anxiety of having to call this, you know, to get the sample back? What's, you know, why do we do missions like this to get samples?
Yeah, sure. So OSIRIS-REx, the name is an acronym, as we like to do at NASA. But every single one of those letters stands for one of our science goals. So it's origins, spectral interpretation, resource identification, security, Regolith Explorer, which you can tell I've said a bunch of times. But it's that it's the origins. And what we really wanted to do was bring back a pristine sample from a very old asteroid. We didn't want one that had come through the Earth's atmosphere and had been sitting on the ice in Antarctica or sitting in the desert somewhere for who knows how long. And we also wanted the provenance. We wanted to know where it came from on an asteroid. So we wanted to very carefully study it and pick that sample site and then bring that sample back knowing where it came from.
Yeah, we knew a bit about Bennu, I guess, before going out and ultimately collecting the sample, mainly from ground-based radar observations. I guess, how did our understanding of the asteroid evolve as we approached closer and closer, and then ultimately, you know, getting that sample?
Is it me? Oh, okay. Well, I think much like our colleagues in Hayabusa 2, when we began to get close enough to the asteroid, as Jamie was pointing out, the first thing we did was kind of scream in our heads because it wasn't what we expected it to be. We expected it from all the scientific data to be smooth with ponds of what we call regolith or loose grains that were centimeter to millimeter size. And it had boulders the size of 11-story buildings on the surface. So we quickly began to get really quietly panicky. Exactly the same thing happened to our Hayabusa 2 colleagues because it wasn't expected at that rendezvous with Ryugu either. So we immediately just regrouped as scientists and engineers do and sit up straight and start planning again at the same baseline, but moving around what we needed to do in order to find a sample site that we could collect, because that was the key point. This was not just to study the geology of the asteroid itself, but to give that geologic context of where we collected the sample, and therefore we had to find, same as Hayabusa 2, a place we could collect the sample. And of course we did, you know the punchline, with our amazing navigation team who got the refinement down to just 1.5 meters or so on the surface, so where they could pinpoint. Exactly the same thing happened with the Hayabusa 2 team. So, yeah.
But to add to that, we also had the Arecibo and Goldstone radar model of the asteroid, which was very accurate. And so that allowed the navigation engineering team to buy down a lot of risk by knowing the shape of the asteroid and how to maneuver around it. But yeah, the actual texture was based on accurate data but incorrect assumptions.
And so we know ultimately the end result, we got the sample back, we got a beautiful picture of it here in our sample canister. So how did the observations from space, from remote sensing, match up with what we actually saw when we got the sample back here on Earth?
Yeah, that was actually pretty interesting because as someone who builds these remote sensing instruments, we don't often get ground truth, right? We're trying to base what we know from the ground-based data and then what we see when we're up close, but we can't really compare it directly to the surface. And so, from the sample perspective, first of all, the sample looks like everything we saw on the surface. Very, very black material, little flecks of lighter material, but the rocks have cracks in them. This is all the stuff we saw on the surface. But, personally speaking, and my instrument was the visible and infrared spectrometer, we were predicting what would be in that composition. And so we were happily vindicated and validated that is what was in the sample. So we were extremely happy with the results.
And just a quick follow-up to that, too. I want to talk briefly about the composition of the asteroid. So when we actually went to collect the sample, we really sunk quite deep into it. It's almost like this ball pit analogy we used to describe how loosely compacted it is. Was that a big surprise? And I guess how did the team handle that news coming through?
Well, we had a range of models, and that was one end member, that the asteroid would be very fluffy. But we focused on the other end member, the pathological one, where the surface was very hard, and we wouldn't get much sample. So that's where our minds were on looking for problems. As it was, the spacecraft sunk 0.5 meter into this ball pit or fluffy snow, only 70 centimeters from the center of the tag ellipse. Amazing. Probably filled up the sample head to over 2 kilograms, which we lost most of it, but recovered double our amount. Out on the table outside is a shape model of one of the big stones that we collected. And we think that's the stone that wedged open the TAGSAM head and allowed material to escape. And I was thinking to myself, this stone had better be worth it. And it looks like it is. Yeah.
Yeah, so Bennu's thrown a lot of surprises at us all throughout the way, including here now as we're starting to look at the sample. So what are some of the first results you've gotten back as you're starting to look through it?
Well, so there's this one stone that I'll let Harold talk about, but we also have seen a lot of organic material, which is my expertise. So the in situ observations predicted at least 1% carbon, and as well as hydration. And we found almost 5% carbon and extensive hydration and a lot of nitrogen. And so we've been able to analyze the sample looking for soluble organic compounds and insoluble compounds. Our lab in Building 34 does the soluble organic compounds. We also found a lot of ammonia, which was a surprise. And I'll also mention one of my great bits of pride is we spent a lot of effort and pain to get a sample of the flight propellant, the hydrazine, which was used as a monopropellant to propel the spacecraft, obviously, and that has an exhaust product of ammonia. And Jamie, who spoke briefly before, was the one who analyzed, put in this rocket fuel into an elemental analyzer, didn't explode, and measured the nitrogen and hydrogen isotopes of the sample. And we're able to compare the nitrogen isotopes of flight's propellant versus the ammonia we found in the sample, and they're profoundly different, proving that we did not contaminate the sample with hydrazine and that the ammonia we detected is actually from the outer solar system, from an icy environment, not from the inner solar system and not from the Earth. Harold?
Yeah, that's wonderful, Jason. I had the good fortune of living in Tokyo, although it was a pandemic time period, but in 2021 for the analysis of Hayabusa 2 as a visiting professor at Tokyo University. And one of the things that struck me, and I saw many Ryugu samples at that time, was how just deep dark the sample is. It's, if you've ever been out on a boat in the ocean or out in a desert and you look up to the sky, and it's really, really just completely dark, except for little twinkles everywhere. So that's what the sample looked like of Ryugu, a cosmos in your hand. And then when we opened up the OSIRIS-REx sample from Bennu, it was the same. But one difference, we had this really sort of visible white material on the surface of some of the rocks. And we scratched our heads and said, well, some of this looks like, Ryugu, some of it looks like serpentinites or stones we see that are very hydrated minerals here on Earth. But what's this white stuff? And this white stuff turned out to be one of the most exciting finds we've had from Bennu. We had hints of it in Ryugu, but it's a very small amount, and it's very small numbers in Ryugu as far as mass goes that was analyzed compared to the large mass we're looking at of OSIRIS-REx. And that white stuff turned out to be one of many evaporite minerals. And it's not just one. In the case of chondrites, which I'm getting ahead of us here a little bit, there's a chondrite in my hand, a carbonaceous chondrite. We see almost no evaporite minerals in these meteorites that are on Earth and collected. But in the Bennu sample, we discovered basically a whole suite of these evaporites, which we could never have seen just from picking up meteorites. Some of them are so delicate that they will react, we know, because we found out the hard way, that they react with the atmosphere very, very quickly and disappear. So the final product, such as table salt and everything, is also what we discovered. So that was one of the most exciting finds so far as the actual rock petrology and petrography goes. It's very similar to the Ryugu, yet very different in other ways. So.
And that rock with the white stuff, that was the one that jammed the head open.
Yes, that's the largest one.
The biggest rock that we got.
Yes, which Christopher Sneed took out of the TAG-SAM head in curation very delicately.
Yeah, it's quite an ordeal to finally pry that open. And I guess one question I always have is, how do you choose, what samples to analyze? You got about 121 grams total. How do you choose what to analyze now and what to allocate for future donations, what to send around, to some of our partner institutions and beyond?
Yeah, that's a great question. That's a coordinated answer because there are a lot of people who are involved in making decisions. So for the science team, we had a baseline plan of analyzing 15 grams of material, which we haven't gotten to yet, by the way. And it's an issue of discussing with the science team what the requirements are for the analysis. Some people need to have the material ground up. So we selected aggregate of material for, say, organics, the fine material, millimeter-sized material, lots of it, in this case 6 grams. And then the organics folks were able to grind it up, make a homogenized powders. Others need very specific size range of particles, so we have to select size range of particles, the whole time working collaboratively with curation, who helps advise us on what is good, what is bad, based on their experience with the sample. And then there's additional sample that the United States government has to work with other governments, such as Canada and Japan, to get them their sample, and they go through a process that afterwards you can ask Kathleen about. She's from headquarters here with curation. And that's how that process is selected. So we XCT all samples, meaning we characterize them in 3D before we do anything to them. so that we maintain as much information about the particle as we possibly can. Even 6 grams of material, we get the 3-dimensional image of it, so that we have that basic information before it gets ground up and dissolved.
And then we actually teed it again after we ground it up to make sure we'd done a good job of homogenizing it. And then that was, again, a coordination between the organic analysis folks and the inorganic analysis folks to come up with a plan that allowed us to analyze both sets of materials without poisoning each other. Because the organic people have one method, the inorganic people have another method, which is mutually incompatible. And so to make sure we maximize every drop of science we can get out of it, and that every bit of Bennu doesn't go to waste.
Yeah, I'll say that's exactly right with respect to even tiny little grains that may fall off that maybe wouldn't necessarily think about picking up. There's somebody on the team who could use that little bitty grain and analyze it.
Yep.
So nothing goes to waste scientifically. Right. Everything is also kept very, very pristine. We should make that point, right? Because the sample is kept in nitrogen inside of Johnson Space Center, and then once it leaves, it's kept in nitrogen in a container, and when it's not being analyzed, it's kept in nitrogen in different laboratories around the world. And that's very important for maintaining the pristine nature of that sample. And as I said, we discovered what can happen if you don't do that, right? The samples begin to react with the atmosphere very, very fast. Same thing with Urugu samples, identical.
And every lab imparts their own kind of contamination. So in our lab, we actually dissolve the sample in solvent, in hot water, cold water, whatever. We make what we call Bennu tea. And so we don't actually care about exposure to air, but we care about exposure to organics, and that's effectively the same procedure.
That's the first time I heard of Bennu tea.
Oh,
Yeah,
Sounds
I like
delicious.
the idea.
it's delicious. No.
I like the idea.
Yeah, so in these samples, in the Bennu tea, you've discovered some pretty fascinating things, like the building blocks of life. Could you talk a bit about what implications that has for, finding life elsewhere in the solar system or beyond, and, kind of what these asteroids could tell us about the larger picture of our own origins?
So we had a number of hypotheses about what we'd expect, and some of them have been right, and some of them have been very wrong. And that's part of the importance of getting a sample. And we wouldn't have been able to tell this from a sample that was in a meteorite that landed on the ground, because they become contaminated almost instantly by biology. And so we were able to detect lots of nitrogen heterocycles, these things, which include all 5 nucleobases found in DNA and RNA, and coenzymes, etc. We also found a whole suite of amino acids, including 14 that are found in biology. And all of them are racemic, that is equal left and right-handed amino acids. Which is, one, interesting because that demonstrates that they're not biological contamination, but also unexpected because we had a hypothesis that we've been working on here for decades that predicted that Bennu should have a left-handed excess of certain amino acids. It doesn't. So our hypothesis was proven wrong by Bennu. Oh well, but that's what we do it, to be surprised. And we'll come up with a new hypothesis to understand. And so this tells us that the ingredients for life were abundant. We already kind of knew that. It showed us that the distribution of these compounds is great and would have been available on the early Earth or Mars, Enceladus, Europa, Ceres, where have you.
And I'll add, because of the abundance of evaporites that we found in the Bennu samples, it's most likely we're actually being able to isolate the main carrier of the organics. We still have work to do on that, but the salts would be the last thing to come out of the solution, which quite probably the sum of the organics are.
So there are several models for the origin of life on Earth. A lot of them involve an alkaline brine consisting of modestly alkaline pH, water, salts, organics. The same stuff we found on Bennu, but there's no evidence of biology on Bennu. So what did Earth have that Bennu didn't? Was it not enough time, the wrong gravity, radiation, evaporation? I don't know, but it's a very interesting question. We have here a model that had all the stuff we thought we needed, but it didn't work out for life. Wow, what a great experiment.
Yeah, I'd like to talk about the fact that, it's kind of a line of thinking. You have prebiotic compounds that you know are needed in order to form life itself and for life to evolve, but there's a gap between the two, and you don't know how you get from one to the other. The one thing you know that is in the gap is a planet. That's it. Because you can't have life without a planet, not as we know it. So that's part of what we're doing as well, is trying to figure out the relationship between all three of those.
And so getting these results and kind of matching them up with what we saw and observed at the asteroid for about a year and a half, did they match up pretty one-to-one, or were there some surprises that kind of came out of what we were seeing?
So Bennu was a challenge in the fact that it was extremely dark. You're only talking 3-4% reflectance. So, it's as black as the blackest thing in this room, probably more so. So from a remote sensing point of view, it was a challenge to pull anything out of that very black signal. And the first thing we saw on approach was those hydrated minerals, in abundance everywhere. So that was a good sign that there was water in Bennu's past. But as we started doing that mapping and getting into the fine details, that's when we started pulling out some of the carbon-based molecules. We got carbonates, we got organics, but we couldn't tell you exactly which one, right? There was a range of them that could be, including those hydrated minerals. The exact one was always a question. When we got even finer than that, we started seeing things like magnetite and iron sulfides, and those were all validated by the sample return. But what we couldn't see were those phosphates and some of those very fragile molecules, some of the sulfides that don't have a spectral signature. So there were still things in the composition we could not tell from remote sensing.
Yeah, and knowing a bit more about the composition from the sample we got back, are you able to kind of return to some of that data and look at some of the sites we didn't choose during that site selection process and kind of see, from orbit, does stuff kind of match up, or are we kind of seeing some things there?
Right. Hydration we saw everywhere. Carbon we pretty much saw everywhere in one form or another. And really the crater we chose was a really representative one with a whole range of different carbonates and organics in it. So I don't think we would have changed which place we sampled because of that. But, like I said, it was very nice validation that these very, very faint signals we were picking out of the spectrum really were there.
And so in thinking about the sample and the asteroid itself and kind of extrapolating that to its parent body, what does Bennu tell us about, formation of asteroids in general?
Yeah, that's a great question. I'll just emphasize what Amy said as well, is that linking what you predicted from the remote sensing to the actual analysis sample, just beautifully, brilliantly linked. So, which really helps validate future missions as well. So Bennu, what we think of as asteroid Bennu, is just fragments of something that we now know was much, much bigger. Go backwards in time, 4.5, 6, 7 billion years ago to the first beginnings of this solar system that we live in, and move ahead a few million years when material is beginning to accrete. Rock is already formed, and soon enough you're generating these large bodies that are even up to Ceres size, that are moving around the solar system. Within several million years, they're beginning to get geologically active in their interior because of the pressure that their rock is feeling, and because they also, in some cases, in the case of carbonaceous material like Bennu, they have accreted ice. Whether the rock and the ice accreted together in the outer solar system, meaning past the snow line, or what was the snow line, Mars, between Mars and Jupiter, or the material moved in. We don't know, but Bennu is beginning to tell us information about that early process of accretion, what the material was like, just like we got from asteroid Ryugu as well. And in the case of Bennu, we have a bit more material than we had for Ryugu, so we're able to look a bit more detail. And it was definitely, and all I'm going to say from the point of view of planetary science, a very big object, what we call the parent body of Bennu, which some of us like to call Nun, which is also a legendary Egyptian part, but that's not official. So we're getting the understanding that this body had water moving through it, Bennu. Its parent body had water moving through it. And it's going ahead doing what it does. The ice melts, it becomes water, moves through, interacts with minerals, and makes new minerals by reacting with the water. And over time, it's behaving itself, and then one day, all of a sudden, bang, it collides with another body, maybe as big as it is, and you make fragments, and it moves around at that point, collects together very quickly, just very fast, a few days even, and then it starts moving through the solar system. So we were able to recreate not only what the earliest stages of Bennu's parent body was like, but the material that actually accreted before, even though Bennu is about 80-odd% to 90% altered from its original composition with water.
And the asteroid has a very unique shape. It's this kind of top-like, diamond-shaped thing. Is that kind of a common thing we might see with other asteroids, out there as well, the way it accretes?
Well, we certainly do see other asteroids with that same kind of pyramid on top of a pyramid shape. And I'm not sure if that's specifically to the carbonaceous ones, but we definitely do see that shape, particularly the ones that spin nicely, kind of get that bulge in the equatorial region. But we have a whole class of others out there that look like potatoes or peanuts. There's for lack of a better analogy, there's quite a range of shapes of the asteroids out there.
And we've really fallen in love with Bennu. We've got all the Bennu merch and stuff and everything like that. But now we're moving our attention to a new asteroid target and actually changing the acronym for our mission. It was OSIRIS-REx for Regolith Explorer. Now we're, changing the ending to Apophis Explorer for our new friend, Apophis. Could you talk a bit about, what the next chapter is for this mission in its extended phase?
Yeah, absolutely. So, of course, when we released that sample, the last thing we wanted to do was follow it in with the spacecraft. So we had to divert the spacecraft right after we released the sample. And it was determined from our brilliant flight dynamicists that we had enough fuel to rendezvous with asteroid Apophis, which you may recall at one point was the most hazardous asteroid out there. And it's going to be making a very close pass to the Earth in 2029 on April 13th. It's a Friday the 13th. You can take that as you will. And it's going to pass between the Earth and the Moon. It's going to be that close to us. So you'll be able to see it naked eye from, probably Africa area. But our spacecraft is currently flying past the sun a bunch of times to catch back up to Apophis and rendezvous with it there.
And so we no longer have our sample return capsule attached that's now sitting in Houston, but there's still a lot of science to be done from a remote sensing perspective. What are some of the observations we're going to be trying to do with a couple of years leading up to 2029?
So we know very little about Apophis. Like I was just saying, it doesn't look like Bennu. We don't have as much radar information, might be peanut shaped, but it also tumbles around. So we're going to be doing that same type of campaign as we did at Bennu, where we try to map it out first, understand its environment, and then try to look at the surface from all angles to understand the composition. But the very end of mission, the plan right now is to descend near the surface. We cannot pick up a sample, but we will fire the thrusters and see if we can excavate material on the surface of Apophis, just as we did on Bennu. But of course, we're not the only extended mission, and I'll let Harold talk about Hayabusa 2's plans.
So yeah, Hayabusa 2 also has an extended mission. I'm not part of it, but I'm very close with the sample analysis team, and we have a co-I from Japan, as well as about, 20 to 30 collaborators from Japan. So the extended mission for Hayabusa 2 is called Hayabusa 2 Sharp. And it has three major goals, and one of which gets forgotten a lot. It's going to two different asteroids, and one is being encountered next year, and then another one in 2031, which is a really fast rotator, about 10 minutes in its rotational axis. And then, and I'm getting old, I have to look at my iPhone to remember the names of both of them, but I'm 60 this year, so forgive me, I've forgotten. One was just renamed recently, 1999 CC2, I think. And then the third part, which is not well discussed, is the analysis of the OSIRIS-REx sample that was exchanged between NASA and JAXA. And the Hayabusa 2 team, a small component of that team, is being reactivated to analyze in the same protocols that Ryugu was analyzed. The Bennu sample will also be analyzed. So that's part of all the extended mission of Hayabusa 2, which would be very exciting. Yeah.
I guess none of this was in the initial plan, which is great that it has this extended life to continue to do the science and continue to, go on further with this. So with that being said, we did get a couple questions in online. I wanted to ask a couple here. So for Jason, how do they make sure that the water you guys add for the Bennu tea does not contaminate the sample?
So everything we do in our laboratory, we run with, well, first we practice everything. Then we run with a positive control and a negative control, as well as the sample. So we have our ultra pure water, which we verify every so often, but we also mix that with a heated up fused silica. We've heated in an oven at 500 degrees C overnight, so that's organic free. We measure that to see what we could have added to the sample. We also have some Murchison meteorite that we've crushed up in the exact same way, and we know what that looks like, so we run that as in parallel. That's a positive control, so we know what to expect if anything has disappeared by accident, and then we run the Bennu sample. And we, of course, make sure nothing is cross-contaminated, and we run everything in triplicate under different conditions, so there are usually 6 to 9 different analyses of each of these. So then we can make sure that everything we did worked right, nothing went wrong, and if something did get added, we know what it is and we can subtract it out.
Yeah, and I want to speak briefly to some of the prep work that you guys did before actually getting the sample back. We, built out a custom clean room in Johnson just to, acquire the sample, and the team went through extensive training to get prepared to go through and make sure everything is super meticulous. If you can speak a bit to some of that work.
Yeah, so, years we spent preparing for the sample return, not just in the sense of planning for various scenarios and planning for the analysis phase of, there's a 390-page document for the sample analysis plan, but practicing. Jason and Danny and their team here on meteorites and developing new techniques. Globally, folks practicing, scientists practicing in different new techniques and refining their techniques and proving that they can do what they claim they can do, to be able to analyze sample from Bennu, and the new facility at Johnson Space Center, building a whole new facility for the Hayabusa 2 sample and for the OSIRIS-REx sample, a whole new clean room with new glove boxes, new protocols. Anybody who went into the clean room, such as myself and Jason, had to go through a training procedure. It's all very, very serious, and we have to make sure we're the best little students in the class, too, in order to get in. So it requires a lot of work by a lot of people who are not here today, who we owe a huge amount of debt to, that are working extremely hard in all branches of NASA, as well as globally in institutions and colleagues at the industry. So, yeah. And we can go on forever about the details, but, it's a lot of work prepping for this. Yeah.
So everyone on the sample analysis team had experience studying meteorites in the laboratory, and or Hayabusa 2, Genesis, Stardust, Apollo samples. So no one came in, I'm going to look at Bennu, that's the first sample I've ever seen, except for students under tight supervision.
Correct.
And I will say that, Jason was also in charge of contamination control during the mission before we even launched. So for those of us putting instruments together, we had to give samples of everything on the instruments for archiving.
Can you talk about the contamination knowledge issue at the Cape? Remember how important that was?
Yeah, so I lived at the Cape before launch for about 5 weeks, and my job there was different every day. Someone would come in and say, in 1 hour we're going to do this operation. We need to use an anti-static material. Which one can we use? Like, in an hour? Okay, I'll figure it out and make the best choice. We did testing of materials. There was one where there was going to be an O-ring that was needed to fit a nitrogen purge on the spacecraft, and everything we'd gone through, I had approved and looked at, or the contamination engineer, who's up there waving his hand, had looked at. Chris Lawrenson. But there's one case where there was one that had escaped our notice, and we had it FedEx back to Jamie to analyze at Goddard, and that was a huge bit of terror, because it turned out that it was filthy, because the bag it was shipped in was the wrong kind of bag. The O-ring was great, but the bag was made out of nylon, and nylon was a prohibited material because it decomposes to amino acids. And so, yeah, we did a lot of work to make sure that the spacecraft was made out of parts we understood, that those parts are archived, so that if someone's doing an analysis in the future, these archived materials that you can analyze, you can also request whatever component is necessary. So I mentioned that we analyzed the hydrazine. We also have an entire thruster from the spacecraft that if you suspected that our analysis of the hydrazine was insufficient, you needed to actually measure the hydrazine plume, what came out of it. You can run that experiment yourself. Just request a sample, set it up. It's $150K to do the experiment, but if it's worth it, then you do it. We have everything there ready for you to go.
Let me just add to that, Jason, because for folks in the audience, there are two aspects of contamination monitoring. The contamination control, which is an engineering requirement, which Jason was intimately involved in with Chris, and then also the contamination knowledge, which was a separate program that the science team implemented to basically double check, just in case, because things happen. So we also archived all that, and in fact, we had a issue after.
Which issue?
Yeah. There's another one at the Cape with SpaceX.
Oh, that, yeah. So
worked out brilliantly in the end.
it was an exciting day. It was September 1st, 2016. We launched September 8th, so this was just a week before launch. We had our fully fueled spacecraft in its vertical assembly building with the solid rocket booster and all of that. 2 kilometers away, the Amos 8 mission to put Facebook in space for SpaceX exploded on the pad during a test. Not everyone was aware that they're doing this test. We had one engineer who was driving past really, really close, and people were showered in rocket fuel from the explosion. It was a terrifying day. One of the most terrifying things for us was that the water cooling pump that shared between the 2 pads was knocked out by the pressure. And so both pads lost water cooling. Well, one was on fire. That was fine. The other one was us. And so we lost cooling. So I was sitting there taking screen captures of the batteries on the spacecraft, getting hotter and hotter in the Florida summer, getting close to their point where they explode. But tanker trucks of water were brought in and cooled everything down before that ever happened. Exciting day. Likewise, all of our prevention techniques to make sure that this plume of black smoke going over our launch pad didn't get into the spacecraft, didn't get in and contaminate the sample. But it was an exciting day.
Well, all the attention to detail paid off. We got the sample back. And, one thing I wanted to ask you about, which I think is fantastic, and something we did with Apollo, too, is when we got these samples back, we don't analyze all of it right away. A lot is stowed away for future generations with the, anticipation technology is going to improve. We did the same exact thing with the Bennu samples. Can you speak a bit to kind of the continuing of science, the future of that for the samples?
Right. So that's first of all, an agency requirement that we preserve 3/4 for the future, which is, for me, my favorite part of the entire mission. Is that people not yet born using techniques not yet invented can analyze the sample and answer questions we haven't thought of or don't know how to address. There is a sample that was, I think it's about 7 grams of material that was removed and has been stored at minus 80 degrees C, will not be open for 49 more years. So that your children, grandchildren, students, or their students can come up with new ideas, new tests, new experiments, and to put us, to build on the foundation that we have and just do things we can't even imagine. I'm so excited to see that in my dotage.
Yeah, we just recently cracked open some Apollo samples, actually, with Jamie's lab. We got some really fantastic results. So excited, set your timers now for 50 years. We'll, check back in and look at some of these samples.
But in addition, every year there's a call. So you don't have to wait 50 years. Yeah. Every year you can request a sample. Yeah. The frozen one, that's put away. But there's a hermetic seal sample. Then there's the majority of the sample has never been looked at except by a camera. And so it's out there waiting to be requested and analyzed. And so one of the things I was told is, as a project scientist and as well as working on the project, you can enable more science to be done than you could do in a lifetime.
Yeah, that's true.
There's always new surprises to come up with this mission. I wanted to ask one more question from online. While I do that, I invite folks to get up to the microphones if you have questions to ask. We'll take some questions from the room here. There's this lesson learned question here. So is there any remote sensing data that could have revealed the loose gravel, the ball pit, as we call it, surface properties ahead of the TAG event?
So I think we had some hints, one of which was from our thermal emission spectrometer. So we measured something called thermal inertia, which is essentially a measure of how quickly something heats up and cools back down. And so you expect a very different number from a solid boulder versus loose sand. And the surface of Bennu was a little surprising to us. And I think that was probably our first hint, that it was a little bit more like the loose sand than like the boulders.
Yeah, and I guess as you continue to observe it, you had, I guess, a year and a half looking through it. There's new surprises popping up along the way. We had to invent, I guess, not invent, but employ the new technique of natural feature tracking, which wasn't intended to be used in the way it was initially. Could you speak, I guess, a bit about that kind of navigation?
Yeah, so originally, I think you might have seen it in the video, we were expecting to find these big smooth areas with about a 50-meter area that would be clear of any obstructions that we could just go down, pick our sample up. The reality is we didn't have anything anywhere close to that big. The whole surface was covered with rocks and boulders. So the best we could do was about 8 meters, which was too tight to let the spacecraft just go down without any checking on the way. But we can't joystick it down. We can't control it. It had to be autonomous. So we employed this natural feature tracking, which took basically a computer model of every single centimeter of the surface from the images from the LiDAR, and it told the spacecraft what it was seeing on the way down. So the images could feed back and say, up there's a boulder, move to the side. So it kind of joysticked itself down, which is really a pretty incredible technique. And that's something we hope to use at Apophis as well, because we don't know what's there yet.
Yeah, and I guess with Apophis, we're going to be using some of the same techniques. Could you speak a bit to some of the instruments that are on the spacecraft, just to kind of give some context for what we're using?
Right, so we have a Canadian laser altimeter, which is really key for measuring that very fine scale structure. We have a camera suite, which can measure from a variety of distances. We have 2 spectrometers, the visible and infrared spectrometer and the thermal emission spectrometer. And everything is completely functional after our Bennu sample. Everything's covered with Bennu dust. So that is one challenge. We have to subtract the Bennu dust off of our images and our spectra. But everything is still operational. And part of getting to Apophis is these close passes to the sun. The spacecraft was not designed for this. So it's kind of our trial by fire. We have a bit of a hero's journey to get out to Apophis. We'll be passing very close to the sun, closer than Venus, 6 times before we get to Apophis. And so we probably gave our contamination control guys a little scare there, and we asked what happens when you get these coatings and surfaces that hot. Things do blister off, but right now everything is fully functional. We've done this twice. We're getting ready for the 3rd, and we'll be getting some of the same great data at Apophis that we did at Bennu.
Fantastic. Yeah, and another question kind of came in here, too, from online. Is there any striking compositional difference between the samples collected from Bennu's equatorial and polar regions? I guess we only got samples from one region, but I guess they're asking, I guess, how they compare to other regions.
Well, yeah, we only got one sample from one place, unlike Hayabusa 2, which got 2 samples from 2 different places. So the answer from sample analysis is, I'm not sure, to be honest. So we focused on looking at the boulders and the geology of the Bennu right now in the collection area. Globally, there are similarities, so eventually we'll get to comparing it all. So there's undoubtedly some similarities without question.
Yeah, another thing too. So I know we found some pieces of Vesta on Bennu. We weren't able to obviously sample them, but we saw them on the asteroid. And I guess what does that mean?
Well, we haven't seen it yet in the sample, but stay tuned. We're still looking. So we know the surface of Bennu is impacted upon quite regularly, right? We have some 1,500 plus impact craters on the surface of Bennu, and it has lots and lots of micro impacts into boulders, centimeter to millimeter size. So it's an active surface with respect to getting pummeled, and of course, material falls to Earth all the time from different places, from different asteroids and different planetary bodies. And it's not necessarily a surprise that you might have something like what we call a eucrite on the surface of Bennu, or some other kind of asteroid type on the surface of Bennu. We find metallic meteorites on Mars as well as on the Moon. So, I mean, they're there. Yeah.
And we also know that Bennu was ejecting particles. We detected right as first approach. They're actually doing an educational public outreach sort of image. They wanted an image of the Earth from Bennu, and the astronomer was looking through those and found these little extra dots of particles that had been injected. I also want to point out to our Canadian contributors that they actually detected the particles first. They were doing some tests of their LiDAR, and they had some returns from off Bennu. I was thinking, well, it turns out they were detecting these particles that are being injected.
Nothing wrong with it. That's right.
No, it worked perfectly, worked so well. And so Bennu is ejecting particles, which makes us think about ways that asteroids could exchange material. Also makes us think that there should be at least very weak asteroid shower from Bennu in the southern hemisphere every September. Hasn't been detected yet, but ought to be there.
Right.
So it's a very dynamic environment.
We did not see that with Ryugu.
Well,
We did not see that we are aware of the ejection events with Ryugu. So
Yeah,
there
I
may
don't-
be a difference in something, the dynamics here.
there's also a different viewing angle. Could
Well,
be that
true,
too.
true, but there may be a difference in the actual,
could be.
dynamics, yeah.
I know it did give us quite a scare initially when we first saw this ejecta in terms of hazardous landing environment to collect that sample, but turned out to be just kind of a beautiful shower of Bennu particles. In looking at the samples too, are you able to kind of get a sense of the depth that they were from in the surface of Bennu? Because I know we went pretty far deep in there before we fired those thrusters to perform the back away.
The short answer is quite probably, but stay tuned. I can't tell you yet. Yes, so we're analyzing samples. So we can analyze samples for their couple of things. How they interact with the sun on the surface, and they get damaged, and called space weathering, and as well as cosmogenic radionuclides, which are different isotopic ratios that they have based on the way that cosmic rays impact on the rocks on the surface versus down below. And so the difference in their exposure ages, we can look at and tell you whether or not they've been exposed on the surface for a long period of time or not. So that's what the process is we're going through right now, yeah.
It's also a dynamic surface. We know that rocks moved around.
Correct.
And things slump towards the equator, and we see trails of slumps, and it's a well-mixed surface, and as we know from the spectra, so confusing.
There's another question that came in. How does Bennu survive larger impacts if it's such a loosely compacted place?
Well, it's definitely got some big impact craters on it that we can see. It's obviously been fairly lucky in its orbit not to encounter anything so big that it would cause complete disruption. So the cosmos has been very friendly to a few asteroids that doesn't happen to. I think that's probably the best way I can answer the question.
If that had happened, we wouldn't have been able to go there. Bennu would be gone.
I was going to say, we made quite a splash at the surface on Bennu, though. I know we were able to take a before and after image between when we got the sample and after. We stirred up quite a lot of particular matter. Was there a lot of science to be gained from looking at those images to kind of see the aftermath of our TAG event?
Oh, absolutely. So we were able to go back and look at the crater inside a crater that we made, and it was, even though it's a black surface, it was much darker and much redder after the fact. So kind of indicative, as Harold said, of space weathering, that we probably threw a whole lot of material that was not as exposed onto the surface. Of course, it was only a quick look. So we know that we excavated a lot of material, so we know that it is a very not cohesive surface, but it wasn't something we could spend a lot of time doing a lot of analysis on.
We have a couple minutes left. I do want to invite anyone if there are questions in the room. Yeah, there's a question here. Oh, yeah, you can go to the microphone.
Congratulations, with this fantastic results of finding organic compounds, amino acids, and nucleobases. Looks like 5 of them. My question is about: did you find any boron, this enigmatic chemical element, boron 10 and boron 11? And if you did, what was the ratio? And also, along with the ratio of nitrogen 15 to nitrogen 14, is there any striking difference from something that we measure in other meteorites or on the moon?
So I can give you the nitrogen answer. It is heavy. It's compound dependent, so the ammonia is much heavier than we see in meteorites. The bulk nitrogen is in the same range as carbonaceous chondrites. Howard, do you want to talk about boron?
I don't know the answer to that question right now, actually. So I'm not sure of our boron isotopic relationships. So,
because it's so important for this important sugars, right? Ribose, for stability of ribose. So it will be nice.
You're using the Benner conjecture about borate stabilizing ribose. That's a separate question, and we have some borate detections, but not isotopically. So that's work to go. I invite you to write a proposal to curator.jsc.nasa.gov.
Thank you. I will try.
Thanks. We've got some more questions on the right here.
Hi, is this on? Okay. Thank you guys for a really interesting panel. I learned a ton. I think it was Jason who mentioned you detected 14 of the amino acids that life makes use of, which I think leaves a handful that were not detected that life uses. So my question is, that gap, does that provide any insights about maybe prebiotic processes or conditions on Bennu versus conditions on the early Earth that would give you insight into the evolution of life?
Well, so first of all, we detected a whole bunch of amino acids, of which 14 are found in biology. Found a whole bunch of other ones as well. The 6 that are missing, some of them are due to the method of their detection. And so we have another procedure that is coming up that Eric Parker will be leading, looking at the more fragile amino acids to see if they're there. That they don't survive well, the formation Bennu T. So you've got to make Bennu cold brew and see if they're
fancy
in there.
now.
It's a trickier technique. It's much less efficient. So you have to be more sensitive. Anyway, that's in the noise. But it has been speculated that maybe the ones that we don't detect are ones that were late in biology. It lines up with some of these hypotheses. I'm not going to go there at this point, but let us finish our work and see which ones are missing and what we can figure out about those. But interesting question.
Very cool. Thank you.
Yeah, another one here, too.
Okay, thank you. Back to amino acids. I'm curious as to why you were expecting more L-rotary amino acids than R, because as we all know, L and R are produced evenly by ordinary chemical reactions, whereas life uses only, I think it's L, but correct me if I'm wrong.
Yep, life uses L. We have looked at a 50 or so different meteorites, and the ones that are the most aqueously altered, we see an excess of L-isovaline, which is an amino acid that's rare in biology, and we've measured isotopically that the left and right-handedness are both the same isotopic number, so it's not contamination. We've measured an excess of left-handed aspartic acid and glutamic acid, again verified by isotopic ratios. These are all in very heavily aqueously altered meteorites. So we hypothesized that, well, if Bennu is also an aqueously altered carbonaceous asteroid, it should also show the same excess. It doesn't. That doesn't mean that all the other detections going back to 97 are wrong. It just means that the reason that they're there doesn't hold up on Bennu. Why there's this excess in some amino acids and some meteorites, always L, never D. There are hypotheses, and well, one of them is wrong. We'll test the other ones. There's also a detection of excesses of the D sugar alcohols that have been done, not yet been done on Bennu samples. That's future work, and D is the kind of sugars you get in biology.
And I assume that in ordinary chemical processes, you get in the sugars an even balance of L and D, just like you get in the amino acids.
Of course, unless you do something tricky like putting in a chiral catalyst.
Okay, that is really weird. I'd like to find out more about that.
So would I.
Oh, I guess one more question here, and then I'll...
Was the surface charged, and if so, by how much, roughly? Was the surface of the asteroid charged, electrically charged, and if so, by how much?
Yeah, I don't know that we had any way to measure that, actually. So.
We have models, but...
Yeah.
Yeah, so we're just pulling up on time here. I had one more quick question to kind of bring things home. I guess for each of you, real quick, what is it that you're most excited for going forward with the sample analysis from Bennu, with Hayabusa 2, with OSIRIS-Apex, and beyond?
Well, for OSIRIS-Apex, it comes down to we don't know what we're going to see, and every time we've gone anywhere, we're always hopelessly surprised and pleasantly surprised. So yeah, I'm really interested to see what that surface is going to look like.
In the words of my good friend and colleague, Shogo Teshibana, who is my counterpart on Hayabusa 2, people like samples. They like to analyze them. So I'm excited about all of it. No one thing, it's impossible.
I still want to understand chirality, but I'm most excited about what future analyses happen of these samples that are waiting to be looked at by people not on the team to read their papers and discoveries that I can't imagine.
So short answer, lots of new stuff to look forward to, lots of new results. You're just getting a little tease of what's to come, plenty to be excited about. I wanted to thank everyone for joining us today for this panel discussion, the first of the year, first engaged session for Goddard. Arigato gozaimasu for our colleagues at JAXA for joining us today. And yeah, thank you so much. Have a great rest of your day.
Thank you.